Okay, good morning to all of you. My screen is visible? Anybody?
Yes, sir.
Okay, thank you. So today we'll see the power MOSFET, that is a metal oxide semiconductor field effect transistor. This is a 3-terminal, 4-layer unipolar semiconductor device. So the layers are N plus, P, N minus, N plus. So that is a 4-layer 3-terminal. The terminals are known to you. That is a gate, drain, and source. Majority carrier devices. This one is a MOSFET, and of course Schottky diode also majority carrier device. And minority carrier devices are BJT, IGBT, and all. There is active device and passive devices. Active device can be control flow of electrons, usually current flow. So that means it is controlling the current flow. It is example SCR, BJT, MOSFET, triac. So all these things come under active devices. Passive devices, it cannot control the flow of electrons like a diode, capacitor, transformers, and all. And the classifications of MOSFET, there is a enhancement type of MOSFET and depletion type of MOSFET. In enhancement, again divided as a N-channel enhancement type and P-channel enhancement type. So all these comes under construction part. I will explain there what is the difference, where we need to change if you want to P-channel or a N-channel. And enhancement and depletion layer types also slightly different will be there. Channel will be present and channel will not be present, like that. So construction of enhancement and depletion both are almost same. Only the thing is in enhancement MOSFET, no channel between drain and source. So that will show the symbol also. There is no direct connection or a contact or a channel. You can see that from drains between drain and source. And whereas depletion type channel, there is a channel will be existing between drain and source. So that is only the difference. Other than that, the remaining all features is exactly same. Only the channel will be present in the case of depletion layer, and channel will not be there between the drain and source. So these are the major difference. Now we can see the diagrams also. This is a N-channel enhancement type. So here you can notice that there is no channel will be established. But whereas here there is a channel is present drain and source. Between drain and source there is a channel will be present, but here it is no channel. So that is a case of enhancement and depletion. So depletion type channel is present, enhancement type channel will not be present. Another difference you can notice, the N channel and P channel, the current directions are different. Now you can see that it is towards, it is outward. So that is the current wise P channel as well as the N channel. Both cases are same. N channel means current inwards, out channel means P channel is current outwards. So this is the N channel MOSFET symbol will represent like this, and then P channel symbol will be only the current directions will differ. So here the arrow, I just mentioned, no, this arrow indicate the direction of electron flow. There is a N channel MOSFET arrow is inwards. See that it is in the inwards. P channel case arrow will be outwards. So that is the difference. And BJT is a current control device, whereas MOSFET is a voltage control device. I already mentioned in the BJT case, BJT it is a current control device. Once if you give the gate current, automatically device will be turn on, base current. So all except BJT, everything is gate. That's why in general I will use term is a gate, but normally in the case of BJT it is a base. If you give the base current, the BJT will trigger. If you remove the base current, BJT will be turn off. So passing the gate current or driving circuit is complicated in case of BJT. But whereas in case of MOSFET, here also the logic is same, but it is a voltage control device. That's why what we want to do is, if you apply the gate and source voltage, if you reach that voltage is a threshold voltage, then the MOSFET will be turn on. And if you remove that voltage, then automatically MOSFET will be turn off. So that's why driving circuit is very simple here. And here, that's the reason we call it as a voltage control device. And low power and high frequency applications we can use as a MOSFET. So these points you can remember for the comparison purpose. There is a BJT case, high power and low frequency applications we can use it there. And the reason is the turn on and turn off times are little bit more in case of BJT. But whereas in case of MOSFET, turn on and turn off times are less. That's why we can easily operate under high frequency operations. And why we call it as a low power application? In case of BJT, the conduction resistance is very less. That's why drops, or you can say that losses are less. You can operate that in the high power applications in case of BJT. Whereas in MOSFET, the conduction resistance is high. That's why if you use this in the high power application, then automatically power dissipation will be more. So that is the reason generally in the MOSFET case, low power application but very high frequency operations is possible. So these are some of the comparison purpose. And when the MOSFET is on, the current flows from drain to source. How it will be turned on, as I said, like voltage applied between gate and source. And similarly, if you removing voltage between gate and source, then automatically MOSFET will be turned off. And this on time and off time in case of MOSFET is very small. That is the reason we can operate this device very high frequency applications. And paralleling is easy due to positive temperature coefficient in case of a MOSFET. Whereas in case of BJT, that is a negative temperature coefficient. So negative temperature coefficient means if the temperature rises, resistance will be dropped down. That is the negative, vice versa in case of positive temperature. So similarly, we can see that in the case of BJT, paralleling of the BJT is complicated because of the negative temperature coefficient. But whereas here, paralleling of MOSFET is easy due to the positive temperature coefficient. So whatever points I am discussing these slides, this is very useful for the comparison between the BJT and MOSFET. I started initially diode, that is a power diode and signal diode. Similarly, later on I started that BJT. I compared BJT and SCR because SCR already covered. And now we start the MOSFET and we can compare MOSFET and BJT. Later on we'll see that IGBT and MOSFET. That is overall comparison, we'll get it. And MOSFET has a high on-state resistance. That's what I told, this will be used for low power applications. So why? Because if RDS is more on the conduction time, the current must be passes drain to source, that is passes through RDS. Then that will lead to a power loss will be more. So that is the reason this will be used for low power application. Now we can see the construction of how this device will be laid and finally how it will be become as a MOSFET. We will see the very scratch one by one step how the device will be established. So now here I explained the N channel enhancement type MOSFET. So we can see the first figure. N-channel enhancement MOSFET, I consider body is a P-type material. So this is a just body or a substrate, both are same, body or a substrate, that I consider as a P-type material. Suppose if you want to make it as a P-channel enhancement type MOSFET, then you can consider body is a N-type. So that is the difference. And consequently, you just see the small differences, whether it is a N-channel enhancement type or a P-channel enhancement type. Only when the construction part, this type of material will change. p-type material and n-type material, that will be reversed because current direction will reverse. That is only the difference. Now, a body is a p-type. Then what you want to do is there is a two n-type material, so that is a two n-type valley are to be created. So this will be one n-type and this is a another n-type material. And then what will happen? N-type and T-type materials, then the depletion layer will be formed because this is one material and there is another material. So then what will happen? There is a depletion layer will be formed between p-type and n-type. So that is the first two figures. For the n-channel type MOSFET, p-type material is a body, and two n-type, we just consider this is for a terminal purpose. We required three terminal. No? What are the terminals? One is a gate, then drain, then source. So that source as well as the body will be interlinked, both potentials are same. So just we'll short that, then we'll make it as a only three terminal finally. Now, so out of two n-type, one act as a source and another act as a drain. So this is the another, because we have taken taps here. So now there is a one n-type material, here is another n-type, and the body, this is a substrate, and now you can connect one terminal. There is a drain, another one is a source. So and the other version, what I told for the p channel enhancement type, what will happen? Here we'll make it as a n and here we'll make it as a p. That is only different for the construction wise. So now we can see that if substrate or body is p-type material, then source and drains are n-type material. Similarly, if body is n-type, then source and drains are the p-type material. So based on our requirement of construction or type of MOSFET, we can change accordingly. In case p-channel enhancement type MOSFET, then what I said, there is a body is a n-type and source and drain are the p-type. So that is the difference in the case of diagram while you are fabricating that. In the third figure, you can see here we'll make it as a n, these two will make it as a p if you change that in the requirement. Now what we'll do is a gate terminal I have to place. So gate terminal is not of direct contact with the body. So these all things are body, no? This is everything is a body. But what we want to do is gate we cannot use direct contact to the body. For that, what you have to do is you have to locate over a SiO2 silicon dioxide. Over that we can make it as a terminal. So that is a thin layer of insulated material SiO2 deposited over the surface of this. This is a body surface. Over that SiO2 you have to place it, and then the gate material, namely we can that material, the terminal is aluminum, is deposited over the SiO2 layer. So now we can see we started with scratch and we make it as a one p-type, then the two n-type material, one is connected to source, one is a drain. Then we need as a gate terminal. For that you have to make it first as SiO2. Over that we connect as a one terminal, that is you just as a metal, as aluminum metal you connected as a gate. Now there is a difference, gate terminal below which SiO2 will be there, below which body will be there. That is a p-type material. So that is in between this area we have like this. There is a two plates, one plate will be upper and lower, and in between this one is a SiO2. So upper side is a gate terminal and metal, body is a another side. So that concept we'll see. So now what we did is we made it as all the three terminals. Now p-type in material, just I'm considering as only the small portion of the gate. What we have, because p-type majority carriers are the holes and minority carriers are the electrons. Now gate terminal more positive with respect to body. We have to connect that such a way that, so you can give the gate upper side is a positive and body side is a negative. First plate, you can see this one, because we made it a positive, no, will appear as a positive charges and offered as a metal contact of the gate. And second terminal, you can see that body. So between where the body will be, in between, it is not a direct contact. That's the reason I said this is a SiO2. We have to make it as a SiO2 in between. Now, gate terminal is a higher potential than the body. That means lower side. So if you apply voltage, the positive charge will be accumulated over the gate plate and negative charge will be accumulated to body plate. So this is the structure will be formed if you apply as a some voltage across gate and body. Now, initially when VGS is low, now we are applying gate and body are a substrate. So then we can see that if that voltage is low, minority charge carriers will accumulated near the surface. And whereas if you are increasing the VGS, uncovering of negative immobile ions will take place. Because of that, holes will be pushed down. You can see this diagram. Now, normally in our case, you can see here. So what will happen? This is a p-type layer, no? So here what will happen? Negative charge particles will be here, and normally there is a positive charge holes will be there. In that holes, what will happen? If you are increasing the voltage more and more across gate and body, this holes will be pushed down like this. Then what will happen? Electrons will reach us to the like this. So that's what the meaning of here. You can see that holes will be pushed down and reach more electrons near to the surface. So that is the upper side. So the negative plate of the capacitor like that. So because of N-type layer, this process is known as inversion. So why I call it as a inversion? Actually, the body is a p-type. When you apply gate and body is a more and more positive, upper side gate is more positive or more voltage, then the body side is a negative, we are increasing that. Then because of this immobile ions, there is a electrons will be reached in the upper side, holes will be pushed down. So then this p-type material will become as a n-type. So that's what the inversion is going to be takes place. So now we can see that VGS is low, so then p-type, and when the VGS is high, then n-type material, due to excesses and negative charge particles, the process is going to be reversed. So that is the known as a inversion process. If you increase the voltage across gate and body more and more, then the inversion process is going to be takes place. Now we can see here, if this inversion is taking place, then this area will become as a n-type, and this is also n, and now there is a channel will be established between these two. So now we can see that because all the area is n-type, no, there is a channel is going to be established. That's what these sentences you can see here. So now once these electrons is pushed, holes are pushed down, then these electrons will reach near to this area, and now this area will become as a n-type. Earlier it was the p-type, and now this is make it as a n-type. So this is same as this. So it will, this area will become as a n-type. So here also n, and here also n, this is also n, this will be established the channel. So now we can see that channel will be established. So once the channel is established, then P and N, there is again depletion layer is going to be formed. So this shaded portion, I call it as a depletion layer. If VGS, the gate and source, is greater than 0, that means positive, or you are increasing, inversion takes place because of inverse conductive channel is formed between source and drain. There is a channel because all the things are n only, no? So now it will be formed as a channel. Now channel is formed, but this is a p-type is there in this side. So here is a n, this is a p, then automatically there is a depletion layer is going to be formed. Once depletion layer is formed, now if you are increasing the VGS, then this layer width will be gradually increases, and finally some certain point of time it will allow current passes through this. So current passes means source and drain, no? So that is only the thing here. Now we can see that increasing the VGS more positive, the channel width or depth will also be increases, and finally some point of time it will pass the current. So that's why we call it as a n channel enhancement. That's now you may be clear that why it is a n channel. When there was no channel initially, because only p type material body and n type materials are the source and drain, but between source and drain no channel will be established, so no current will pass through that. But later on, when gate terminal is made positive with respect to body, then we noticed that channel is enhanced. That's the reason earlier it was not there the channel, now the channel is enhanced. That is the reason we call it as a N channel enhancement type. Suppose if it is a P channel enhancement MOSFET, what will happen? Body will be as a N and P will be there in the same process, will be in the reverse direction. Then what will happen? Initially there is no channel, later on then the channel will be established, P channel. Then that is the reason we call it as a P channel enhancement. So that is only the difference. So now, so source and body are connected internally. That's what I told. No, whatever terminals we have, the source terminal and then body terminal. So these two we can short. So there is a, here will be source terminal. You just short with the body terminal, and this is a drain will be there, and here is a some SiO2 over which there is a terminal aluminum, that will be as a gate. Now we will make it as only 3 terminals. That's what the same potential, you just short it. If VGS is increased, width of the channel will also increased. One point of time, that means VGS is greater than the threshold voltage. Threshold means triggering voltage or turn on voltage. That much voltage is required between gate and source, then it is going to be trigger. Then what will happen? Channel width is sufficient to allow the current, because that will be width will increase while you are increasing the voltage. Some point of time, what will happen? The current will passes from drain to the source. So this particular voltage we call it as a threshold voltage. That's what when the MOSFET is going to be triggered, if gate and source voltage is more than the threshold voltage, then the trigger the MOSFET and also increase the current, so drain current. So now this is the final diagram of your MOSFET. So now we can see that these two will be shorted. This is the source terminal is directly short to the body, because this is same potential. Now I have to apply gate and source voltage. This is a gate and source. We need to apply. Gate terminal is positive with respect to body, I told. No, that means body is in turn connected to the source. That's why I connected directly. Here is a voltage source. To pass the current from drain to source, we required some voltage. So therefore you connect some voltage source across drain and source. So this is the internal diagram, final structure of a MOSFET. So if the mass is a N-type enhancement type, so individual step by step we can explain, or if you are familiar, directly you draw this circuit and explain one by one process, whatever I explained so far. So this is the step by step. P material is a body, and 2 N-type material, that is a drain and source, and then there is a gate terminal, and internal how the inversion is going to be takes place. Then channel will be established, and there is a depletion layer will be formed, and after that we have to connect this body and source is one, and you have to give the voltage, and to pass the current we required as a drain and source voltage potential. So that you can all these here 3 and here is 4. So all these things diagrams you can put it in the exam and you can just explain. And now there is a small pinch of voltage. Now we can see that what is that pinch of voltage? Controls a current between two terminals, that is a drain and source. using gate. That we aware that. Now by controlling that voltage, the current is going to be controlled. So there is a simple capacitor structure using P-type substrate and the metal gate, like previous inversion I explained. No? So if you apply positive potential to the gate, then what will happen? Electrons will be attracted to the gate. And if the voltage is VTH, that is a threshold voltage, then under the gate there is additional electrons. That means N electrons will be more than the holes, then metal will be N type metal. So now what will happen? The gate voltage greater than the threshold voltage. If that voltage is greater than, then there is a N-type region between the source and drain will be formed and channel will be established. So that path will be established from source and drain region. Then what will happen? That region we call it as a channel. So once the channel is formed, there is a resistive path between the source and drain. So because it will not be directly passed, there is some resistance between that channel. So there is a channel will be formed, there is N and N. So in this and here, then automatically will be formed as a one channel. So that channel, there is a resistance will be path, that path, some resistance will be present. So the resistance of the channel is proportional to the width to length ratio. So the channel resistance is proportional to the width to the length ratio. We can place a voltage between source and drain, cause a current flow. That's why I mentioned in the structure case, we need to provide between source and drain, there is some voltage source to pass the current. Now, you can see that. So it's the same as that. So we can see that the channel, if the increasing that voltage, there is a resistance path will be there, and this end of this channel will be vanished and it will be length will be decreases. That's what you can see that. One thing, note that the drain voltage rises. So means because we connected drain to source from voltage source, no. So if that voltage is rises, results in a thinner channel at the drain end. So this is the can see that if we are increasing the voltage in this side, the channel will be very, very thinner. So this portion is only the pinch off, nothing else that. So now we can see that thinner channel will be at the drain end. Therefore, what will happen? Channel thickness at the end of the drain side will be the 0. This is called as a pinch off. So that edge will be as a very thin, and finally that thickness will be 0, and then reducing the length, that will decrease the resistance, because at the end of that finally there is a thinner and finally it will be vanished, then the length of that channel will be reduced, that will be decreasing the resistance, because R is equal to rho L by so that length will be reduced, then automatically resistance also will be reduced, and hence it will allow the high current flows through that. So then the effect of pinch off is that the channel no longer act like a simple resistor. Then the current becomes fixed once that is saturated, the value prior to the pinch off. So once if it is saturated, the current will be remains the fixed one. When the transistor is operated in a saturation region, this phenomena is called as a pinch off or pinch occur. So that means the normally we will operate under either cutoff region or a saturation region. So that is completely on or a completely off. So this is the only that portion separately I drawn how the pinch will be affect. This will be reduced at 0 level. Now we can see the characteristics. So input characteristics as well as the output characteristics of a MOSFET. So N channel E MOSFET, that is an enhancement type. That meaning is N channel enhancement type MOSFET. Now here you can see that there is a the characteristics for the input side. We can see that ID, this is a input current, and then VGS we need to apply to trigger the device. So we can notice the diagram itself. So what will happen if that voltage, VGS voltage is below the threshold voltage, the device will not trigger. The device is not trigger means that what? No current. If the device is trigger, only current will pass like this, no? So that's why we can see that this value is less or below some 2 to 3 volts, then automatically the device is in the off state. Now, once if the increases the voltage VGS, if this voltage is increased beyond the threshold voltage, so as I said, threshold voltage 2 to 3 volts, then what will happen? The device will trigger and current will be gradually rises. So this is the characteristics of a input MOSFET. I mean input characteristics of a MOSFET. So then you can see that output or a drain characteristics. So we can notice one thing here. So what will happen? The cutoff region. So cutoff region VGS is 0. If VGS is 0, it won't be trigger. So that's why it is nothing but a cutoff region only. If it is not trigger, something like turn off. Now, so if VDS, that is drain to source voltage, is larger than the breakdown voltage, then what will happen? The MOSFET will break down due to the avalanche breakdown. So here, even though if we are not increasing the gate source voltage, if drain source voltage increases beyond the breakdown voltage, automatically avalanche breakdown will be takes place, then the junction will be turn on. So that means the junction will be forward bias. The output characteristics, you can see that 3 regions. One is a saturation region, then ohmic region, and then cutoff region. So we'll operate either in the cutoff region or in the ohmic region. So only these two operations is going to be takes place. So when drain to source voltage is small, that means this voltage is small, then the relation between drain current as well as the drain to source voltage is linear, and MOSFET operate under ohmic region. So this region, so MOSFET will operate under ohmic region. So that means it is a turn on process. And now if the operation that will operate under ohmic region, then VGS must be greater than the VGST. That and drain to source voltage also must be greater than 0. It should not be 0. If you pass the some voltage applied across the drain and source, then only current passes through the drain to source voltage. So this device turns off or cutoff region, and the device is on means ohmic region. If it is off means cutoff region. So that is the 2 points. So now in active region, the drain current ID does not depend on the VDS, but it varies with the gate source voltage. So only the thing is we don't operate normally in the active region. So that is other application, but in our application we don't be. So if ID saturated current, the region is called as a saturation region. So this region drain current can be expressed with some relations. I made it. Drain current is proportional to the square of the difference of VGS minus VGST, and K is a constant that depends on the internal parameter. All these things will be takes place. Now we can see this is as I said now, the before threshold voltage VGS, it will be off state. Once it is occur threshold voltage, then the avalanche breakdown will be takes place, device will be triggered, and then current will be gradually rises. Similarly, in the cutoff region, the again same phenomena. If the voltage is below that, it will be turn off, and then we can see that VGS is 0 case cutoff region, and we are increasing the VGS to 1 point, another point, and so on. We can get these characteristics. That is a output characteristics between the IDS and then VDS. And this is the case for the P channel enhancement. Only the difference is currents. I can see that what will happen, the VGS is negative we are applying because the directions will change. So now it will be threshold, after threshold it will develop in the negative side, and this also you can see that VGS we can make it as a negative in case of a P channel. Earlier characteristics I shown as a N channel enhancement, now it is a P channel enhancement. And that drift region, all these things, why will RDS will be high? You can see that RDS is nothing but a VDS by ID. The on-state power resistance of MOSFET is RDS. That will be high in our case, MOSFET case, that is VDS by ID. Some of the drain resistance and then drift, because layers are all, inside there is a drift, N-1 drift region also will be present. Then channel resistance of source resistance is nothing but a RDS will increase. So low breakdown voltage, all resistance components contribute equally, and then on-state resistance that determine the on-state resistance. When the breakdown voltage, this is a VDSS, that is a breakdown voltage, is greater than the few hundred volts, then N minus drift resistance, that is RD, will contribute the maximum of the total RDS. So whereas earlier it will be small, now if the VDS is a greater breakdown voltage, then the drift region resistance will be added more, and that will contribute to the increasing the RD. So this resistance of drift region RD is a function of a breakdown voltage. So now the breakdown voltage, if you want to more, then the RD will get it contributed more. So since the RD depends on the VDS, the value of RD is increases. This is only the major problem in case of a MOSFET. Preferably in any device, conduction drop must be less, because once the device is conducting, it carry the more and more current, because load current, it has to carry the current, load current it has to carry. That's why if that resistance is more, automatically what will happen? The drops will be takes place. So the drops leads to the efficiency of the device as well as the total control setup will be the reduces. That's why under higher application the MOSFET won't be used in this case. On resistance also depends upon the junction temperature, because this is, I said, no, when you compare to the BJT case, there is a negative temperature coefficient, but it is a positive temperature coefficient if it is also depends on the temperature. If the temperature, if you are not controlling, then the temperature will rise also, resistance also going to be high. If the resistance is high, again dissipation is taking place more. That version will come, because the power carries to that RD, and the dissipation during on condition, the power dissipation is like this. So RDS in the total on resistance and type of this value will be something 9 to 100 milliohms. So this is the resistance preferable value of that, and power dissipation will be like this during on condition. So this is the just simulation of that. Once the gate is given, then the device will trigger, and gate is removed, means gate source voltage, nothing but. And now switching characteristics of a MOSFET. Like a BJT, switching characteristics is nothing but a during on and during off. That is only the difference. Whereas when you compare to other one, other in the sense static characteristics and all VI character. But here there is some time is required, no, 30 to 300 nanoseconds of time like that. So to turn on the device, what will happen, or that process only we notice. You can see here, first if you want to on, what we want to do is you have to provide as a gate signal. So this is a gate signal. So before the gate signal, the device is off state only. Once if you provide gate, then automatically device is going to be trigger. There is a two terminal, or you can say the two intervals. One is the delay time, another one is a rise time. So TD is a delay time during on process or turn on delay, during which input capacitance change the charge to the threshold voltage VGST. So that means if that plates across that is reaches to the VGST, that means it is ready to trigger. So before the VGT, it will not be triggered. That is the delay time, or you can say that turn on process, sum of the delay time and rise time. TD is a turn on delay time, during which what will happen, input capacitance charge to threshold voltage. So that is the first term. Another one is a rise time. So there is a rise time, gate voltage rises to the VGSP, that is a voltage sufficient to drive the MOSFET or to trigger the MOSFET. and drain current rises from 0 to full load current. So drain current, when it will be according to our structure operation, once the channel is established, sufficient width is allowed, then the current will passes through the drain to source. So but you have to connect as a voltage, positive terminal to the drain side, negative terminal to the source side. So therefore, if that is sufficient voltage reaches gate and source side, then VGP, that is also threshold voltage, then the drain current will drain current will pass. So drain current is nothing but means that the device is completely on state. So that is some of the delay time, and then rise time we call it as a turn on time. So now the rise time can be reduced using low impedance gate drive source. So low impedance means high current will pass. It will take less time to get it as a required voltage. So for that reason, we can say that this sentence will be time can be reduced using low impedance gate drive source. And this turn on time will be 1.6 microseconds. Now you can notice that when compared to other devices, as I said, in the case of SER 1 to 4 microseconds of time, and here only 1.6 or almost very less turn on time. 1.6 means it is just very short duration you can able to turn on, and also off time. So if the turn on and turn off times are less, then automatically switching frequency will be more. Once switching frequency is more, then what will happen? You can operate this device under higher frequency applications. So turn off process is initiated soon after removing the gate pulse. Now you can see that at T1, when if you pass the gate source voltage, then only the on process will be initiated. And similarly, when the off process will be initiated if you remove the gate, like a voltage, nothing else. Gate source voltage, if you remove, automatically device is going to be turn off. If you give the gate source voltage, it will be turn on, like that. In between, you can see that this is a source voltage is present. Now we removed that at this point. Separate pulse I am showing here. If you remove that, what will happen? This current, you can see that this current will be gradually decreases and reaches to the zero level. For that also the two intervals will be there. So at T1, mentioned here, turn off process initiated after soon removing the gate pulse at T1. So because pulse is removed. So there is a delay time, means off process is the time during which input capacitance discharges from our drive gate voltage V1 to VGP. So there is a V1, it is a voltage, and finally it is reaches to the VGSP, threshold voltage. So if this is the sufficient breakdown voltage, if it is below threshold voltage, what will happen? The device is going to be turn off completely. So now the fall time is the time during which input capacitance discharges from VGSP to VGST. So below threshold voltage. So if it is below threshold voltage, now it is reaches to this level, automatically you can see the current is reaches to the 0 point. So that is the process. Now the sum of these two we call it as a turn off time. So turn off time is 30 to 300 nanoseconds of time, but on time is 1.6 microseconds of time. These are the some of the empirical relations. You can see that power loss. So this will be power loss during off state, and this is the average power loss during on state, and average power loss during off state, and the power loss when the device is under on state. So there is a sum of instance what is the power losses will be. So that is very small amount of losses only. It is not a significant, but in the case of semiconductor device aspect, you need to consider. But once if you use this in our controller, when compared to the load and all, these losses are very negligible. That's why efficiency of these controllers efficiency of the device, we can say that very high. It is more than 99%. So nearly 100% it will reach. So because it is our minute drops. Now you can see that merits of MOSFET. It is a majority carrier device, and have positive temperature coefficient, hence paralleling is possible, and turn on and turn off times are less, then high frequency operation is possible, do not require commutation circuit, whereas in SCR we require commutation circuit. Here it is not required because once if you remove the gate signal, automatically device is going to be turned off. Gate has full control over the operation. So now it is easily to control. Either you have to pass the gate voltage or remove the gate voltage, the device is under our control. You can see the demerits. On-state loss will be high because RDS is more. Only low power applications because power loss is more, and suffer from static charge, that is then between there is a capacitance will act that will charging and discharging takes place to turn off the device. While it is turn on, it will charge, and while it is turn off, it has to be discharged. And application, you can see that high frequency and low power inverter application, and SMPS you can use, and inverter and chopper, because preferably for the DC application side we'll use as a MOSFET and IGBT and all, and AC case you can use thyristor, but DC case if you use thyristor, commutation problem will arise. That is the reason preferably we don't use thyristor in the case of what you call it as in the DC side. So that's the problem actually, but the MOSFET we can use it. It is a voltage control device. So low power AC and DC drive applications only we can use it, because why I mention low power, because of the power dissipation is more than compared to. So now we can see the comparison between BJT and MOSFET. It is a current control device. BJT is a current control device, and MOSFET is a voltage control device. Output is controlled by controlling the base current, because base is given, it will be on, and remove, it will be off. And whereas MOSFET case, output is controlled by controlling the gate voltage and negative temperature coefficient in the case of BJT. All I mentioned in the while I am explaining that points you can remember, and you can make it as a chart like this. We'll get it as a differences. So here will be paralleling of this device is easy, and then dry circuit is complicated, but here dry circuit is simple. Losses are low because conduction resistance is less there, that's why conduction losses are low, and here conduction losses are high in case of MOSFET. And the BJT case it will be used in high power application, but MOSFET case low power, and then BJT have high voltage and current rating, and MOSFET will be less ratings only, and switching frequency is lower than the MOSFET, but switching frequency is higher in case of a MOSFET. And secondary breakdown occur, that we can see that serious problem in the BJT case. The avalanche breakdown will be takes place, high temperature dissipation is going to take place in the secondary breakdown. That is the major problem in BJT, and here it will not be there. And high switching loss, but conduction losses are less. Here the point is switching losses are different and conduction losses are different. That is very important note we need to consider. Switching loss means during on and during off, that we call it as switching losses. Conduction losses means if the device is on condition, completely on, it is under operation, the whatever loss will be occur, that will be call it as a conduction loss. But you can see in the BJT case, so there is a high switching losses during on and during off, but once it is conduct or it is on completely, losses will be less. So but switching time is very less, but conduction time is more. So here you can see that low switching losses but conduction losses are more. So that is the case of different between this BJT and MOSFET. While it is on, there is a RDS will be more, we'll get it as a conduction losses are more, but during on and during off losses are less in case of a MOSFET, whereas in case of BJT is high. That is the another difference. There is a high current rating compared to the MOSFET. So current rating is high, that's already I told, no? So higher application we can use as a MOSFET, but BJT will be used higher application, MOSFET will be as a low application. And now we can see that depletion type n-channel MOSFET. So there is a enhancement type we observed and depletion type of the different. You can see that here the channel will be present. I will show that one by one layers also. So this is the same as gate, but the gate operation will be differ here. In the depletion type, MOSFET can also operate as a enhancement type also if we give as a gate is positive. So that is only the possible case in the case of depletion type MOSFET. There is a gate is 0, you can make it, gate is negative, gate is positive. So three operations is possible in the case of a depletion type MOSFET. I will show that one by one. Now you can see as usual this diagram construction will be exactly same. Only the thing is gate terminals will change. You can see now body, substrate, and then N type material will be drain and source, and then there is N channel will be established here, and you can connect. Now the from here onwards there is a difference. What will happen? There is earlier what we did is gate and source, we make it as a gate is positive with respect to the source, we connect like this, and we increase the gate and source voltage there. So now here is a three modes of operation is possible in depletion type n-channel MOSFET. And once if you know n-channel, p-channel, nothing is there, just you change that body type material, all these things. Now we can see VGS is 0. That means we shorted gate and source. So VDS, that is the drain to source, increases, ID will increase normally. If we apply the voltage between drain and source, that is essential anyhow to pass the current. But here we are not given any gate voltage, VGS is 0. Then after some time, drain current will become constant if you pass the VDS voltage. And another one is there are two actions happen when the VGS is negative. First case is VGS is 0, you just give the gate and source voltage and it will be pass the current. So that is one operation. The second case, VGS is negative. If VGS is negative, there is a two actions will be takes place. So first one is electrons in the N channel are pushed down, whereas in the case of previous one, there is a holes are pushed down. Now electrons are pushed down. If you give as a this one is a negative. If you give this one is a negative, then automatically what will happen? Electrons are pushed down and holes will be reaches to that layer. So that is the difference. And P substrate are what we call it as attracted towards the gate. So then what will happen? Due to this recombination between the electrons and hole will occur. Because of this, what will happen? There is a available electrons from conduction will decrease and hence ID will decrease. So we can see that there is a N here, this will be as electrons, but now the holes will be reaches to this, then the recombination is going to be takes place and current will be decreases. That is the case of VGS is a negative. Now VGS is positive as usual of a what you call it as enhancement type of MOSFET. So that is the reason this depletion type of MOSFET can operate as a both enhancement type also possible by given, that is a third case, by given as a gate is positive. So that's what mentioned here. Construction of depletion type MOSFET or N channel is we noticed in the previous diagram. In this highly doped N plus region are diffused into the lightly doped P minus substrate. There is a N plus region will work on a source and other will work on a drain, and in between all these processes are same. In between SiO2 will be placed, all these things. So that is there is no different in the operation when compared to the enhancement type and then depletion layer type. Only the thing is what we can operate that device enhancement type also, means depletion can also act as a enhancement type of device also. That is the difference. And the characteristics wise you can see that this is the different of case of depletion, because this can act as enhancement this can act as a depletion mode. If you give the gate is positive, that's why this characteristics we can notice that there is a depletion type, VGS is negative. You can notice that VGS, if we give negative, this will be act as a depletion. Now if VGS is positive, it can act as a enhancement type. So this is the case of depletion type. Both can operate, either gate is positive or gate is negative. So that's what I mentioned here. VGS is 0 and VGS is negative and VGS is positive. So in that all the three regions of operation is possible. So drain characteristics of DMOSFET in the sense depletion type, and values below VGS is 0, and the set of curves, that's whatever graph we mentioned here, this will be operating under a depletion type as well as the enhancement type of MOSFET. And these are the characteristics. We can easily see that by seeing the symbol of that, we can easily notice that what type of, because if channel is present, you can see that between drain and source, this is called it as a depletion type MOSFET. And the current direction, based on the current direction, you can say that whether it is a N channel or a P channel. Based on the channel, we can decide whether it is a depletion type or a enhancement type. Now we can see that if we short all these lines, we can say that it is a depletion type, and current is in the outward, then it is a P channel. So current is in the inward, it is a N channel. Similar case of enhancement type, N channel means current is inward and P channel means current is in the outward. So these are the characteristics. Also we can notice that positive or negative. Depletion type, we can get both. Means enhancement also possible, but whereas here these two we can see that it will be only in the what you call it as enhancement type. This is just for a glance only, I made it that. And safe operating region, when the device is going to be operate safely. So at what conditions? Because the device is under operating side, that is SOA, represents the maximum value of current and voltage at which MOSFET is safe. Because here operating regions are what, when you are operating device in some application, at what voltage and at what current because all these devices are very sensitive in the current aspect and all, voltage and current. So while you are operating, this is within the specified limits only we have to operate. That means safe operating region means only those areas we can, but a very small time we can able to operate with a little bit more currents and voltages, but the region we have to identify. For that we mention here, we have to operate voltage and current within the specified region only, that is a safety purpose. So as per the specifications of MOSFET, there is a maximum drain current, ID maximum, and then internal temperature they will give, and breakdown voltage is known to you, and maximum power dissipation, PD maximum. So these are the some of the parameters we need to consider. In that safe operating region, the graph we represented here, ID versus VDS, drain to source voltage and then current. We can notice in the MOSFET safe operating region, the region is going to be little bit different with respect to the time. You can see that time case, there is a safe operating as a power MOSFET drain current ID and VDS are represented in logarithmic graph sheet. You can see that 0, 10, 100, 1000 and so on, it will get it. So solid line shows the boundary of the DC operating point. So there is a DC, this is the line. You can see that for the while you are operating as a DC, this is the region we can get it as a safe operating region. And when the device is being used short duration, so here also based on the time also we can decide the region. You can see the sentence is very clear. Short duration, the power dissipation is less and junction temperature is low, and boundary of this safe operating area will increase. Now you can see that suppose if you want to operate as a 1 millisecond, this is the boundary case. If you are operating only 0.1 millisecond, you can get it more area, and then 0.01 millisecond. That means the difference is very simple. While you are operating as a load test of a machine or anything, once if you are loaded more and with long duration, if you run the machine, that's why in our load test and all, we are using water and pulley. We are pouring some water pulley. Then what will happen? You can see that why you are using the water there to you are operating as a machine under a long duration. The power dissipation is takes place, that is in the form of temperature rise, and the heat will be developed in the armature winding. So to cool that, we are using as a water there, so just cooling purpose. But you are you fully loaded or even overloaded with the fraction of 1 minute or 1 second, then it won't be happen, so it will be allowable one. So that's the reason you can see here this point of times 1 millisecond, 0.1 millisecond. If you go on increasing the operating time is very very less, so you can allow some more current also, because after all it is very very less time, it won't be happen anything. So that is the operating regions is going to be changed once the time will be changed. So these are the safe operating regions. So now we'll see the next one, IGBT, in the next class. So today at moment we'll stop at this point. And if you have any doubt, you ask me, and if possible, we will conduct afternoon or maybe evening time. Are you willing? Anybody? At 5 o'clock or something you are ready, then I will take one more class. Anybody?
సార్ రేపట్లా తీసుకోండి సార్ మళ్ళీ.
Sure, then okay, no problem.
Yes, sir.
Tomorrow
Thank
anyhow
you,
I
sir.
have class.
సార్
I will
కానీ
take
లాస్ట్ అవర్ ఉంటుంది కదా సార్, రోజుకి 5 క్లాసెస్ ఉంటున్నాయి.
okay, okay. You have free hours?
ఒక అవర్ ఫ్రీ ఉంది సార్, లాస్ట్ది 3:30 to 4:30.
Okay, no problem. Then today you can enjoy.
Yes, sir.
Okay.
Thank you, sir.
Okay. You can leave now. I will take attendance.
Yes, sir.